Human civilization, from early structural engineering to the modern clean energy grid, is completely dependent on a sequence of 10 specific transition metals. This animated diagram of the periodic table isolates those exact building blocks, elements 21 through 30, spanning from scandium to zinc. These 10 elements set the exact physical limits of our engineering, technology, and biology. It starts with scandium, element 21. It is a rare, highly lightweight metal required for manufacturing high-performance aircraft and illuminating powerful stadium lights. Next is titanium, element 22. It offers the strength of steel at the weight of aluminum, making it an engineering necessity for high-stress aerospace applications and biocompatible enough for human medical implants. Securing the supply chains for these two lightweight metals is a strict prerequisite for any future advancements in high-speed, high-performance mobility. Moving to the heavy builders, vanadium, element 23, is the structural alloy that reinforces the massive steel beams required for vertical skyscrapers, while also enabling next-generation energy storage. Chromium, element 24, provides extreme corrosion resistance. It is the core metallurgical property behind stainless steel and highly durable, brilliant protective finishes. Manganese, element 25, works alongside them to further strengthen commercial steel and drive the chemistry inside modern batteries. Element 26 is iron. It forms the highly abundant structural base of global cities and macro-scale engineering projects, while serving a dual biological role by carrying oxygen through human blood. Without the specific metallurgical enhancements provided by these builder elements, vertical urban expansion and the long-term survival of our physical infrastructure would be impossible. Element 27, cobalt, is the blue metal responsible for the high energy density required to operate electric vehicles, smartphones, and large-scale clean energy storage. Nickel, element 28, withstands the harshest industrial environments, fortifying both specialized stainless steel and electric vehicle battery chemistries. Element 29, copper, is the world's most efficient commercial electrical conductor. It distributes power from massive generation sites directly to homes, cities, and renewable grids. Finally, zinc, element 30, acts as the universal protector. Industrially, it shields steel from rust through galvanization, while biologically, it operates daily to fortify the human immune system. The global shift away from fossil fuels relies entirely on our ability to source and harness the highly specific electrochemical properties of cobalt, nickel, and copper. From the structural limits of our cities to the electrochemistry of the clean energy grid, these 10 metals are strict prerequisites for a functioning modern society. As this heat map visualization of the periodic table shows, controlling the supply, refinement, and application of these specific elements is the primary hurdle for future industrial expansion. We do not simply build with period 4 elements. Their physical properties dictate the absolute boundaries of human progress. Period 5 transition metals, from yttrium to cadmium, are the strict, non-negotiable raw materials required to power modern infrastructure, aerospace, and clean energy. To understand how we build the future, we have to isolate elements 39 through 48. Mastering this specific 10-element block is essential. They represent the specific material requirements for advancement in aerospace, medicine, and global power generation. The sequence starts with yttrium, element 39. It serves as the baseline foundation for powering advanced materials, brilliant lasers, and vibrant digital displays. Next is zirconium, element 40. Its extreme strength and corrosion resistance makes it a trusted necessity, relied on for both life-changing medical implants and high-stress energy generation. Element 41, niobium, acts as a hidden strengthener. It is critical for reinforcing rockets, jet engines, and enduring intense wind tunnel testing for the future of aerospace. Born in ancient volcanoes, element 42, molybdenum, is now required to produce the world's strongest steels. It handles the physical stress placed on the interior turbine blades of advanced propulsion systems. Element 43 breaks the natural sequence. Technetium is the first artificially created element, serving a singular purpose, allowing doctors to medically diagnose millions of patients globally every year. This first half of the period 5 block provides the material solutions for surviving extreme physical stress and achieving internal medical visibility. The block then shifts to rarity and chemical precision. Element 44, ruthenium, is a rare platinum group metal utilized for durable coatings and advanced electronics. Rhodium, element 45, is one of Earth's absolute rarest metals. While known for giving jewelry its brilliant shine, its primary industrial function is cleaning our air. Element 46, palladium, possesses a unique chemical capacity to store hydrogen. This specific property positions it as a primary engine for tomorrow's clean energy technologies. Silver, element 47, is nature's most reflective metal. Its technical value lies in its necessity for building complex space exploration hardware and high-precision electronics. Finally, cadmium, element 48. Extracted from hidden earth minerals, it is used in high-efficiency solar panels to capture the power of sunlight. Elements 44 through 48 mark a clear transition in utility, moving from brute structural strength to high-efficiency energy capture and precision chemical manipulation. This matrix categorizes the 10 elements into 3 distinct strategic application sectors, summarizing their global impact. The aerospace and alloys cluster, zirconium, niobium, and molybdenum, forms the foundation for extreme environment engineering. The tech and clean energy cluster, yttrium, ruthenium, rhodium, palladium, silver, and cadmium, acts as the chemical driver for global sustainability. Finally, the medical cluster, powered by zirconium and technetium, provides the essential tools for diagnostic imaging and human life extension. The pace of development in these critical sectors is determined by how effectively we secure and master these 10 transition metals. Modern engineering in aerospace, energy, and medicine is constrained by the physical properties of a specific sequence of chemical elements. This section of the periodic table isolates the period 6 transition metals, spanning elements 72 through 80. Understanding this 9-element sequence is a requirement for designing hardware that must survive extreme thermal and mechanical stress. Hafnium, element 72, is used to regulate the internal temperature of nuclear reactors and shield aircraft at the edge of space. Tungsten, element 74, functions as a thermal guardian. Its melting point allows rocket structures and industrial components to maintain integrity under intense heat. Rhenium, element 75, is exceptionally rare but essential for jet engine turbines, allowing them to operate at temperatures that would liquefy standard industrial alloys. Osmium, element 76, is the densest naturally occurring element, utilized in environments requiring extreme pressure endurance and manufacturing precision. The current capacity for hypersonic flight and deep space transport is defined by the thermal and structural limits of these 4 metals. Tantalum, element 73, enables the miniaturization of life-saving medical implants and the electronics that support global communication networks. Platinum, element 78, acts as a chemical catalyst to accelerate clean energy production and filter environmental pollutants from industrial exhaust. Modern engineering utilizes gold's corrosion-resistant conductivity for electronics and deep space hardware, the same chemical stability valued by ancient civilizations. Global connectivity, energy sustainability, and medical longevity are currently dependent on the chemical reliability of this specific trio of metals. Iridium, element 77, is a rare metal concentrated in planetary impact sites, utilized for its ability to endure the most corrosive environments on Earth. Mercury, element 80, is the only metal naturally liquid at room temperature, a property that established it as a foundational tool for atmospheric and thermal measurement. These chemical anomalies prove that rare origins and unusual physical states provide unique, irreplaceable utility in specialized engineering. The combined properties of elements 72 through 80 define the current performance ceiling for rocketry, medical infrastructure, and clean energy systems. Engineering progress in these sectors rely on the continued availability and mastery of this transition metal sequence. Looking at this specific block of the periodic table, the transition metals from atomic numbers 104 to 112 represent a distinct category of matter. You won't find these elements in nature. They are entirely synthetic, built in laboratories by smashing atomic nuclei together to test the physical limits of how atoms hold together. By forcing these super heavy elements into existence, researchers can measure atomic behaviors that differ from those of lighter, more stable matter. The sequence begins with rutherfordium, element 104. This is the first transactinide, a classification marking a new tier of elemental weight. Breaking past the actinide series opened an entirely new physical space for chemists to map. Next is dubnium, element 105. Because it degrades so rapidly at this mass, it has to be synthesized and analyzed essentially one atom at a time. Operating at this scale allows scientists to physically probe the absolute limits of modern chemical engineering. Pushing further, researchers named these new elements to record their history. Element 106, seaborgium, directly honors American chemist Glenn Seaborg. This marked the first time an element was named in honor of a living person. Element 107, borium, is named for physicist Niels Bohr. Its synthesis helps scientists observe the specific physics governing the universe's heaviest atoms. Element 111, rhenium, honors Wilhelm Röntgen, continuing this lineage as researchers measure matter at its most extreme mass limits. This block of the table functions as a permanent log, honoring the scientists who developed the methods to create these elements. The heavier the element, the shorter its lifespan. For hassium, element 108, researchers must rely on single-atom chemistry just to observe how its electrons behave before it decays. Meitnerium and darmstadtium, elements 109 and 110, ranked among the rarest materials ever created, demanding atom-by-atom synthesis for even basic study. At the far end of the sequence sits Copernicium, element 112. One of the heaviest elements ever made, it exhibits chemical behaviors that diverge from expected periodic trends, providing a physical stress test for modern chemical theory. There are no commercial applications here. The value of these materials is the raw data they provide on how matter behaves at maximum density. Taken together, the period 7 transition metals are defined by their extreme mass and the atom-by-atom engineering required to create them. By creating elements that do not exist in nature, scientists gather the specific data needed to map the physics of the universe's heaviest atoms.